Okay, this is 1.3 and 1.4. 1.3 deals with atomic mass and basically its relative atomic mass and how it is found and calculated. So, mass spectrometer is used to measure the mass of an isotope, and we'll compare that mass of each and break apart the isotope and see how much of that isotope is present in that sample. Here's an example of one. Zirconium has a molar mass of 91.3, which is an average of all the isotopes. You can see that the most abundant isotope is around 50%, a little higher, of 90 zirconium, or zirconium 90. How you figure out how a mass spec actually works. You have to ionize the sample, meaning you have to turn it into an ion, whether it's a positive cation or a negative anion. It has to be vaporized, and it's accelerated through a tube, which is surrounded by magnets, positive and negative side, and the one gets deflected. The higher the deflection, it means it's lighter. The smaller the deflection, it's a heavier isotope. Here is another example of a mass spec. You have magnesium. There's three isotopes. The most abundant you can see as magnesium 24 at 79%. And then two others at 25 and 26 are relatively the same at 10 and 11% respectively. So, if you know what isotopes are present and in what percent, you can figure out the mass of the atomic or atom. So how do you do that? Looking at the isotopes, we have three isotopes written at form. You have magnesium 24, magnesium 25, and magnesium 26. Notice they all have 12 on the bottom because they're all magnesium, and magnesium has 12 protons. The only thing changing is the number of neutrons. Determine the molar mass. So again, we use the same picture, and we have to basically just solve it like you would figure out your grade in your class that has different percentages worth different points. So for magnesium 24, it's worth 79%. So you multiply by the decimal of 79, which is 0.79. And isotope 2 is 10% of 25, so 0.1 times 25. And then isotope 3, 11% of 26, and you add everything up. We get 24.32, but you gotta remember we're dealing with science, so you gotta deal with significant figures. So remember, when you're adding things up, you always go by the least precise, which is the 2.5 number, which is the 10th spot. So you can only go to the 10ths, which would be 24.3 grams per mole. Here's some practice problems. You got two of them. One is just to write the isotopic formula for the heaviest isotope of germanium. So looking on the picture on the top right hand corner, you want the heaviest one, which would be the far right one, and that is going to be at 76. So 76, making sure you know that germanium has 32 protons, so it goes in the bottom. 2b is to use the abundance, so find all the using all the abundances, find the atomic mass of germanium. So you have 5 different isotopes. So each one gets multiplied by its percent, and you add everything up, and you should get 72.5 grams per mole. So make sure you can do that on your calculator, pen and pencil, and make sure you get the correct answer. Alright, 1.4 deals with the mole, amount of substance. We use moles, we'll get into that. So, atom is very, very tiny. So our electrons, molecules, formula units, basically everything in this that we can't see is dealing with chemistry, is very, very small. We notice the changes, but an atom is very, very small. So we use a mole to scale up this small mass. So it makes things a lot easier with numbers. What is the number that relates to moles? Just very small things like atoms and molecules and electrons. If you said Avogadro's number, you are correct. And what is Avogadro's number? It is 6.0221415 times 10 to the 23 is his number. You can call him if you want to, but he won't answer because he is not alive. And that's not actually his phone number. Anyway, we use 6.022 or 6.02 most of the time in chem. I like 22 because it has 4 sig figs. So, how do we use Avogadro's number? Well, a mole of atoms is 6.022 times 10 to the 23 atoms. If you have a mole of molecules, it is 6.022 times 10 to the 23 molecules. If you have a mole of particles, if you guess 6.022 times 10 to the 23 particles, it's not a guess because you are correct. Same thing with formula units. It is Avogadro's number of 6.022 times 10 to the 23. So everything that deals with a mole, it's just like working with a dozen cookies. A dozen cookies always means 12. If you're working with a mole, it always means 6.022 times 10 to the 23. More working with Avogadro's number. Here we got sodium atoms. Again, a mole of sodium atoms is 6.02 times 10 to the 23 atoms. A mole of fluorine, same thing, 6.02 times 10 to the 23 atoms. A mole of sodium chloride would be 6.02 times 10 to the 23 molecules. Notice the difference in units. It's still the same value, but we're working with different units. Mass using the periodic table. You should know the molar mass of sodium looking on Na is 23 grams per mole. Fluorine is around 19. And if you add up sodium chloride, you get 58.5 grams per mole. Relating molar mass again to atoms, molecules, and ions. If you have a mole of sodium, it is 6.02 times 10 to the 23 atoms of sodium. A mole of sodium chloride is the same value, 6.02 times 10 to the 23 sodium chloride units. If you're dealing with ions, same thing. It's 6.02 times 10 to the 23 ions of both sodium and chlorine. The reason why the number is still the same is because sodium chloride is a 1-to-1 ratio. It's 1 sodium for every 1 chlorine. So 1 molecule of sodium chloride is also equal to 1 ion of sodium ion. Just looking at the formula itself, NaCl. There's 1 sodium, there's 1 sodium ion. Same thing with chlorine. Chlorine is 1 chlorine and sodium chloride, and therefore it's 1 ion of chloride, Cl minus. One thing you gotta be careful about is chlorine atom and chlorine molecule. Molecule is more than 1 atom, so that means it's not the same. It's just not Cl. It's Cl2. It's diatomic. So a mole of chlorine atoms, yes, is 6.02 times 10 to the 23 atoms, and a mole of chlorine molecules is double that. Reason why it's double, again, remember, chlorine molecule is Cl2, so it's twice as many atoms in Cl2 than in Cl. Oh, I already said that. Diatomic, remember the 7 diatomic elements. Here's the math involved in that. 1 mole of chlorine is 6.2 times 10 to the 23 molecules per mole. And in 1 molecule of chlorine, there's 2 atoms of chlorine. The mole map. Everything goes through mole land, moleville, mole town, whatever you want to call it. Notice all the arrows point to moles. So if you go to atoms, to molecules, formula units, you can go to moles. If you have grams, you can get to moles. If you have a gas, you can get to moles. So mole land is always important to understand, and which one you're using. If you have something small, you need a big number like Avogadro's number. If you have mass, you need to use the formula mass or molar mass, you want to call it. And if you have a gas, you use there's 22.4 liters per mole or 24 liters per mole, depending on the specifications of temperature. We'll get to that later, though. So again, you can go through mole land to get to Atomville and Mass Town and whatever you want to call them, but you can always go through moles. So if you go in atoms to moles or moles to atoms, you use Avogadro's number. If you're going from moles to mass or mass to moles, use molar mass. Here's some practice. Check out number 3, page 5. Calculate the amount of moles in the following. You have 10.7 grams of sulfur atoms. So, in dimensional analysis, you start with your given. You draw your box and lines. And since you're dealing with mass, you're going to use the molar mass. Molar mass of sulfur is about 32 grams, and that's for 1 mole. Notice the grams are across from each other, so they will cancel out. And you simply divide the number, and you get 0.335. So make sure you know how to do that. Make sure you practice that, not just look at the PowerPoint. Here's 3A, calculate the amount of moles of a sulfur molecule, S8. Same setup, you have your given. The only difference is now you're not dealing with molecules. So S8, you have to look up the molar mass of sulfur times 8, which is 256.528 grams. And that's for 1 mole. Divide, or cancel out the grams, and then divide. You get a 1/4 mole of S8, so 0.25. Number 3 again, part 3, we have iron nitrate. Find the amount of moles of iron nitrate, FeNO3, iron 3 nitrate. You have your given. You find the molar mass of iron nitrate, which you should get at 241.86 grams. 1 mole of that. Cancel out your grams. Do your division. You should get, again, 0.250 moles of FeNO3. Again, make sure you practice, not just look at the video or PowerPoint. Use your pen and pencil and paper, calculator, good to go. 3B, calculate the amount of atoms and 7.10 grams of chlorine atoms. Okay, chlorine atoms, that means it's not diatomic. You start with your given. You have mass, so that means you got to go through molar mass, which is 35.45 grams per mole. That's from the periodic table. Grams will cancel out. So we have moles now. So we continue our DA. We got to put moles on the bottom. And since we're going to atoms, which is very, very tiny, we need a very, very big number. And that is Avogadro's number, 6.022 times 10 to the 23. Moles cancel out. Do your multiplication, which would be the two top numbers of 7.1 and Avogadro's number, and divide by the mass of 35.45, and you get 1.21 times 10 to the 23 atoms of chlorine. Alright, we're at the end of our section, so this is your homework problem that you will need to complete and turn in. If you have any questions, you can always go back on the other examples in the video or in your text, or you can always email me if you need any help. Those are your answers to check your work, but you have to show your work to get full credit, well, all credit. And I'll